Okay, welcome to the operations research course. So for this course, we'll continue with our linear programming, but we'll focus more on how to solve mixed constraints type of linear programming problems. And so stay with me as we move on with this. All right, so in our previous two lectures, we had looked at solving maximization problems and also solving minimization problems. And we have used constraints of the standard form. So the maximization problem, we saw that all of them actually are in the standard form, the problem or at less than or greater than constraints for the system of constraints, and the non-negativity rule being greater than or equal to 0. Yes. Then also in the minimization problem, we realize that all the inequalities in the constraints were less than or equal to 0. And again, the non-negativity rule still applies as the greater than or equal to 0. So however, let's consider a problem where we have a mixed type of constraints. So with the knowledge that we have from the maximization and minimization problem, we shouldn't have any problem with mixed constraints types of problem. All right, so let's say that we want to maximize a function which is 20x1 plus 10x2, right? And this function is subject to x1 plus x2 is equal to 150, x1 is less than or equal to 40, and x2 is greater than or equal to 20, and as usual, x1, x2 are greater than or equal to 0. That is the satisfy the non-negativity rule, right? Good. So this is a typical mixed constraint problem, right? Why? Because it has an equal sign. It has a less or greater than inequality or constraint, and it has a greater than or equal to also constraint. So although it is a maximization problem, right? So the simplest procedure actually will be to solve the problem, and at least we talk about the steps in forming the problem, that is transforming the problem into a standard form, right? Then to determine the initial solution, determine the initial solution into the tableau. Then step 3 will be so initial solution. Then step 3 is undertake the iterations. Then step 4 is to repeat 3 until there is no better solution, right? So until there is no better solution. All right, so for us to convert or to transform the inequalities, right? Let's pick the first one. X1 plus x2 is equal to 150. So x1 plus x2 is equal to 150. So here, you may think that x1 plus x2 is equal to 150 is actually a standard simplex form, but it is not. Why? Because if the initial solution, so if x1 is equal to 0 and x2 is also equal to 0, right? Then what it means is that 0 plus 0 is equal to 150. This is actually impossible, right? Or it is actually not true, right? Not true. So therefore, what do we do? Remember in the minimization, we saw something like that. So since an equal sign indicates a strict condition, so where there are neither unused resources, right, nor the possibility of overachieving a specific requirement, right, slack or surplus variables are not appropriate. So we shall remember our artificial variable. So let's use our artificial variable to take care of the realistic, constraint here. That is at the origin, and meet that straight equality constraint. So for instance, we will say that x1 plus x2 plus the first time we are using artificial variable a1 is equal to 150, right? So with this one, we can test and see that if x1 is equal to 0 and x2 is equal to 0, that is at the origin, right? That is at the origin. Then it means that a1 is equal to 150, right? a1 is equal to 150. So this satisfies, well, this one actually makes sense, for us to use the artificial variable. Now let's look at the second one. X1 is less than or equal to 40. So x1 is less than or equal to 40, right? It's actually similar to a typical maximization problem, right? So we know that if this is so, it will be x1 minus a slack variable, we can say s1, right, plus a2 is equal to 40. Okay, so we are using s1 here, not because it's in the second constraint, but because it's the first time we are introducing a slack variable. So we are using surplus 1 or s1, right? We are using s1. So the next one will be no, so this one is the minimize. This one is just like the maximization. So we got to. So it's rather x1 plus s2 is equal to 40. What this means that if x1 is equal to 0, then s2, let's use s1. First time we are introduced, then s1 is actually equal to 40, right? So it's supposed to be plus, right? Yeah, supposed to be plus. Then the next one is x2 is all the cost is greater than or equal to 20. x2 is greater than or equal to 20, which is a minimization, right? It's a minimization. So this one will be x2 minus s2. I'm using s2 because this is the second time we are introducing s2 in the equation, right? Good. Or in the model. Then plus a2 is equal to 20. So a2 is also because we are using that artificial variable for the second time. All right. So what this means is that our new model, right, the transformed form is 20x1 plus 10x2, right? And is subject to x1 plus x2 plus a1, which is equal to 150, x1 plus s1 is equal to 40, x2 minus s2 plus a2 is equal to 20. And because we have introduced s1 and s2, then they add nothing or they contribute nothing to the objective function. So it will be plus 0 s1 plus 0 s2, right? Then it's a maximization problem and we have artificial variable a1 and a2. So we want to use the big M. Remember, big M is very big. And because we don't want it to contribute to the function, it should be negative big M a1, right? Then negative big M a2, right? And because we have introduced new functions and new decision variables, then we'll say that all of them, x1, x2, s1, s2, a1, a2, they must all satisfy the non-negativity rule. So at least this is the transformed model, right? So this is the transformed model. So we then find the initial solution, right? So we then find the initial solution, and using the simplex, which we are used to at this stage, right? We draw our normal tableau. We draw a tableau, and so I'm sure you're familiar with this. So we have CJ, CB, bases, then the BIs, then we have so these three. So I have my CJ here, I have my CB here, I have my basis here, I have my BI here. So I have X1, X2, S1, S2, A1, A2. All right. I think that's it. I have X1, X2, 1, 2, 3, 4, 5, 6. All right. So do that, do that, I do that. We have that, and we have that. Okay. So for the objective function, we have 20, 10, 0, 0, big M, big M. So we have 20, 10, 0, 0, negative M, negative M, right? Then here we have the ZJ, then the CJ minus ZJ, right? It's a maximization problem. And we say, how do we get the initial solution here? So we get the initial solution from here, right? Based on what we know already. So the first constraint, A1 comes into the solution. The second constraint, S1. And the third constraint, A2. So we have A1, S1, A2. So to populate that, we have A1, S1, and A2, right? And A1, what is the coefficient here? It's negative M. S1 is 0. A2 is also negative M. All right, so what is the BI? For the A1, that was, I think, 150, 40, 150, 40, and 20. So we have 150, we have 40, and we have 20. All right, and what are the contributing parameters of the constraint here? So 1, 1, all the rest are 0. So I have 1, 1, 0, 0, 0, 1, then 0. Then for 40, 1, 1, the rest are 0. So 1, 0, 1, 0, 0, 0. Then for the third constraints, 1, negative 1, 1. S2, A2. So 0, 1, 0, negative 1, 0, 1. All right, so we solve for this, right? Which, as usual, we know negative M times 50 plus negative m plus 20 plus 0 times 40. And so that will be 150, 20, 170 m. So negative 170 m. And this one also gives us negative m. This one gives us negative 2 m. Then we have 0, we have m, we have negative m, we have negative m. So Cj minus Zj will be Cj 20 minus negative 20, so that is 20 plus big M. Then this one is 10 plus 2 big M. 0, 0 is 0. 0 minus M is minus M. Minus M minus M should be 0. Minus M minus M should also be 0. Right? So again, look at the trend. We have S1 in solution and it's 0. We have A1 in solution and it is 0. We have A2 in solution and it's also 0. So these are some of the things that you use to check yourself whether your tableau is correct or not. All right, so let me get rid of these marks. Yeah. Let me get rid of that. Okay, so if we have this, right? So then we ask ourselves, which one is the entering decision variable or the entering non-basic variable, right? So we look for the largest. So the largest Cj minus Zj, and that is 10 plus 2m because 2m is bigger than 1m, right? So this one is entering into the solution, right? So that is our pivot number, right? So this is our pivot column, right? So we have to look for the pivot row so that we can get the pivot number. So the pivot row is obtained by dividing the BIs by the pivot, the numbers in the pivot column. So 150 divided by 1 is equal to 150. 40 divided by 0 is equal to infinity. Then 20 divided by 1 is equal to 20. And because 20 is the minimum, right, is the minimum, then it means that that row is actually our out, which is our pivot row. Very simple, right? So this row is our pivot row. Therefore, this number is our pivot number. That means that A2 will be leaving the solution basis and it will be replaced by X2, right? Go. So our next tableau will be with that. All right. So at this point, I believe that we can all solve this based on our experience in solving the simplex using the tableau, right? So we can all solve this. So we just need to create our Cj, Cb, our basis solution, our BIs, right? So we have that. we have that, we have this, we have that, and that. Yeah. So this is x1, x2, s1, s2, a1, a2, right? And this is zj, cj minus zj. So we still have a1 in solution. We have s1, a2 has been replaced with x2, right? So the coefficient here is 20, 10, 0, 0, negative m, negative m. So I have my 150 here, 40, 20. Now this is going to change, right? So we don't have to fill this now. So we have to fill this negative m, 0, and s2 is 10. All right. So we knew the pivot's number to be 1. So we divide everything here by 1. So it means that all the values we have here stay the same. So 20, 0, 1, 0, negative 1, 0, and 1. Right. So for us to complete the second constraint, right, to fill it, is the old number, right? The old number, so we know the drill already. The old number minus the corresponding pivot number here, which is 0 times the new number, right? Which is 20. And because it is 0, because our corresponding number here is actually 0, right? Because this is 0, you see that everything will also stay the same, right? So this is the trick that you use to be able to move fast in solving some of these solutions, right? Okay, so 1, 0. Remember, A2 will not come in solution, so there's no need to stress myself by computing for A2. A2 left the system, is out, right? So no need to calculate for or fill the tableau for A2. All right. Now, the value here is 1. It's 1, so it will just be 150 minus 20. So when you work, you get that 1, the whole number, 0, 0, 1, and 1. So it works this way. So when you now complete the 0, you have 200 minus 130m, right? Negative m is here. Pin, 10. 0, 0, 0. So this is 0. Again, remember S1 is in solution. A1 is also in solution, right? Good. And so S2 is not in solution, so negative m and negative 10. So that is negative 10 minus negative m, and that is that. Good. So 20 minus that will be 20 plus m, right? 10, 10, 0, 0, 0, 0. That S2 is 10 plus m, and this is it, m. So now we find the entering pivot number, right? So we find the entering non-basic variable, which is that. So x1 goes into solution. Why? Because that is the highest. M. We have M here, we have M here, but we have 20, which is bigger than 10. So therefore, x1 goes into solution, goes to replace which of the non-basic, which of the basic variables. Will it replace A1 or S1 or X2? We actually do not know. So this is what we do. 130 divided by the pivot number, which is called 130. So this is the pivot column, right? So this is the pivot column. All right. Then 40 divided by 1, which is 40. Then 20 divided by 0, which is very large, infinity. So this is actually our pivot number. And this is out, which is our pivot row, right? So we are done with this tableau. So when you finish it in this form, then you say that you are done with the tableau. You can move on to the next tableau. So you can see that A1 is still in solution. So, and we've not gotten any better solution. So let's continue our iteration. So in the next iteration, we have we still have something. I want to see this so that I can trace that. So we still have this and we have that. So A2 is out of the solution. So we won't worry our time and strength computing that. So BI Z X1. So normally I want to do this. CJ, CB, the basis solution, the BIs, the basis solution, the BIs. So then we have X1, X2, S1, S2, A1. All right, so that S1, A1. So we still have this and we have that. So this is ZJ, this is CJ minus ZJ. Now we populate, so we have 20, 10, is it 20 or 40? It's 20, okay, 20, 10, 0, 0, negative M. All right, 20, 10, 0, 0, negative M. Then we have A1 is still here. Now S1 is being replaced by, so S1 is actually being replaced by X1, right? So we'll have X1 here, and this is X2. Okay, so what's the coefficients of the basis solution here? A1 is negative M, X1 is 20, X2 is 10. So, so X1 is the solution variable, so that means that goes first. So we divide all the numbers in the second constraint by the pivot number, which is 1. And so the value there remains the same, which is 40, 1, 0, 1, 0. So remember, A1 is still in solution, so there's no need to cancel this column out. Okay, when it leaves solution, then you take it out. But now it's still there, so you leave it there, right? So for us to recalculate for A1 or the first constraint, which is that, right, is actually 130. right? And the corresponding number is 1. So that means that it will be 130 minus 40, which is 90. The period number is 1. 1 minus 1 is 0. Then we have this one to 0, negative 1, 1, and 1. Then x2, the corresponding number is 0. So everything remains the same. Remember, 20, 0, 1, 0, negative 1, and 0. 20, 0, 1, 0, negative 1, and 0. Yep. So we compute this and we have 1000 minus 90m, negative m 0, 2, 1, 0. So this one will be 20, 0, 0. This one will be 10, negative m 20, m and 20. So that will be 20 plus m, negative m, negative 10. So this will be negative 10 minus that. And A1 is that. So Cj minus Zj, 2020 is 0. Remember, X1 is in solution. So I'm expecting that the unit change in the contribution will be 0, right? Good. X2 is also in the solution. So 0. Now 0 minus that is 20 minus m, right? Then 0 minus that is m plus m, and that is 0. A1 is also in solution, right? Good. So here, do we have a better solution? Yes. How? There is a positive contribution from S2 entering into the solution. That is Cj minus that, because this one is positive. That is the pivot column, right? Is in, right? So X2 will be entering into the base solution, and which one goes out? We actually do not know. So let's divide all the BIs by the numbers in the pivot column. So 90 divided by 1 is 90, right? 40 divided by 0 is infinity. Then 20 divided by 1 is negative 20. So which one is the least positive value? That is this column, that this row, the first constraint. So therefore, this one goes out, and therefore that's the pivot row. That's the pivot row. All right, and therefore, this is our pivot number. So S2 is going in solution to replace A1. So someone is asking, why wouldn't S2 go and replace A1 at the second iteration? So this is the simplex. You see that when we use a different method, like the two-phase method, it may have changed. So the number of iterations can change depending on the type of method that you used. Okay, so for this case, we have S2 going in solution to go and replace A1, which is in solution. So S2 is non-basic variable to replace that. So what we'll do here, let's take this back to number, right? So this is our final tableau here. So our next iteration will be to replace S2, to replace A1 with S2. So if we are to draw that tableau, right? And it's interesting when you see such happenings, because you actually do not want any of the artificial variables in solution. So it's interesting when you see that they are being replaced, then you know that you're actually getting some realistic numbers or real values. All right, so we have that. We have this and that. Yeah, as for the tableau, you should be able to draw it with ease at this point, right? Okay, that So we have x1, we have x2, we have s1, we have s2. Okay, should I bring a1 and cancel it? Yes, it makes sense to bring a1 and just cancel it out. Right? All right. So what is the so here is zj, this is cj minus zj. All right, so x1 is 20. I'll have to draw these lines before. Yeah. Okay, so 20, 10, 0, 0, negative m. Yeah. So a1 is being replaced by s2. So now we have s2. Then which one was the x1 and x2? So x1 and x2, right? So what's the coefficients for the s2 in the objective function is 0, x1 is 20, x2 is 10, right? And now the bi, we calculated 90 here, right? So you bring that here, 90, or you look at the pivot number and you divide everything by the pivot number. So because it's 1, everything remains the same, which is 0, 0, negative 1, 1. Then there's no need to compute for a1. So now we can cancel it out. When you do this, at least you understand that a1 will not enter into the solution basis again. Right. Good. So what do? We recalculate for x1 is 40, and remember is 0. The corresponding number here is 0, right? So we know what to do. All the numbers will stay the same. So 40, 1, 0, 1, 0, right? And here is negative 1. If it's negative 1, then all the numbers will add to the next. So 90 plus the old number was 20. So that will be 110, right? So we have 0 here, we have 1, we have negative 1, and we have 0. So how do you then compute your z? 0 times 90 plus, you see how clearer it is. So this surplus, which is not, or the slab variable not adding anything to the objective function, the maximization problem, is contributing 0. So though the bi value is 90, is contributing nothing to the z function, right? So the z function then becomes 20, 40, 10, 110, and so that's 1,000, 800, so 1,900, so 1,900. Here, this one is 20, this one is 10, right? And 0, 20 is negative 10, so that is positive 10, 0, 0, 0, and that will be 0. So we have 0, 0, negative 10, 0. All right, so now we search for the pivot column. We'll see that the pivot number column, we said that is the largest cj minus zj, positive, right? Cj minus zj, there's nothing here. So therefore, since there's no largest positive cj minus zj, it means that anything that enters the solution basis will actually not give us a better solution, right? So this will be the fourth tableau will actually be our final tableau or our final solution, and therefore we say that the solution is optimal. So since the solution is optimal, or the optimal solution then is x1 is equal to 40, x2 is equal to 110. Sometimes you can make meaning out of this and say 40 units, 110 units, and there is a surplus from the resources in the second constraint, S2. Is it the second constraint or third constraint? Let's look at the equation. S2 is here. So it's in the third constraint. So there is a resource left in the third constraint. And how many? 90 units, right? And the Z, or the function, is actually 1900 units, right? It's actually 1900 units. So this is what to do with mixed constraints, right? This is what to do with mixed constraints. All right. So before we move to the next lecture, there is a summary of what to do when you see the various inequalities. Yeah, when you see the various inequalities. So I'll share my screen and we will see what I have on the slides here. So close this whiteboard and bring this screen up. In summary, if we have a constraint which is less than or equal to constraint, right? If you are dealing with a maximization problem, we actually add a slack variable, right? You add a slack variable and the coefficient in the objective function is 0. If it's a minimization problem, you also add a slack variable, but the coefficient is also 0. If it's an equals to constraint, you add an artificial variable, and if it's a maximization problem, you put in a negative m as the coefficient in the objective function. But if it's a minimization, you put in a positive m so that it doesn't go into solution, right? Or it doesn't affect the function. Then if the constraint is greater than or equal to inequality, right, you subtract a surplus variable and add an artificial variable, right? But for the artificial variable, you use negative m in the objective function if it's a maximization problem, and use positive m if it's a minimization problem. So I think that will end this lecture, and thank you very much for staying with me. We'll meet in the next lecture. Cheers.